In this video we will introduce the base model which is used in the wind farm application examples. Activate the study case base model. Here you can see the network model. The network consists of 6 individual wind turbines, each supplying the 20 kV network via a step-up transformer. At the point of common coupling, there is an external network, and at the wind farm's substation a capacitor bank is connected. Let's take a closer look at the wind farm substation. Right-click on the buzzbar and select Show Detailed Graphic of Substation. On the top left part of the wind farm substation detailed diagram, the PCC is shown, which is part of the distribution network. The separation between the distribution network and the wind farm is indicated by the property line. Furthermore, the 4 switch bays of the wind farm substation are illustrated, showing the location of the 2 cable overcurrent protection devices and the wind farm voltage protection. Let's go back to the overview diagram and look at the wind turbines in more detail. Each wind turbine is identical. They have a nominal apparent power of 2.778 MVA and a nominal power factor of 0.9. A dynamic model has already been applied to each of the wind turbines. You can access the dynamic model via the icon highlighted. On the Load Flow tab you can see that each of the wind turbines has an active power set point of 2.5 MW, and an external station controller applied. On the Operational Limits tab you can see that a capability curve has also been applied to the wind turbine models. A station controller acts on each of the wind turbines in the network to control the reactive power flow. The station controller can be accessed as shown. On the load flow page you can see that the station controller applies a cos phi as a function of P characteristic. When the active power at the controlled node is 7.5 MW or less, the overexcited power factor is set to 1. When the active power at the controlled node is 15 MW or more, the underexcited power factor is set to 0.95. Between these active power set points, the power factor decreases linearly. In the table on the Distribution tab, you can see each of the wind turbine generators and the proportion of the total reactive power that each is supposed to supply. The point in the network at which the power factor is controlled is determined by the highlighted parameter. We will introduce a new wind turbine model to the network. First, unfreeze the graphic. Place a point node in the network as shown. We will place the node halfway along the cable. We will now introduce an appropriate wind turbine template. We want the template called Fully Rated Converter WTG 2.5 MW. Select the template, click once in the screen and connect the template to the point node. Notice that the template is already configured to deliver 2.5 MW of power. Notice as well that the capability curve and the dynamic model have also both been applied by the template. If we now run a load flow on the system, you will notice that the new wind turbine is generating 2.5 MW of active power and no reactive power. If you look at the other turbines, you will see that each of those is absorbing an amount of reactive power, 0.8 MVA. The new turbine has not been included in the station controller, so we must add the turbine to the station controller. Right-click on the turbine and select Add to and then Station Control. There is one station controller in the network model and you should select this one. Take another look at the wind farm controller. You can see that the new turbine is at the bottom of the list. Run another load flow. You can see that the active power at the point of common coupling is around 17 MW. This is the amount of power fed into the grid. Cos phi is being controlled to 0.95 according to the characteristics that we applied in the wind farm controller. The value of cos phi is negative because the active power is being transferred from the wind farm to the 20 kV grid. Notice that the new generator is now absorbing reactive power. The reactive power absorbed is equal to the reactive power absorbed by the other generators. Since we have introduced the new generator, we should update the parameters in the cos phi as a function of P characteristic. If we increase the active power to 17.5 MW to reflect the new generator and rerun the load flow, you will notice that the active power at the point of common coupling is not exceeding the set point. As such, the power factor is not quite equal to 0.95. In fact, it has increased from the previous value in accordance with the linear power factor characteristic.